Alright, not really sure what time it is right now, so I felt like recording a video real quick. Well, not really real quick, but yeah. Alright, let's just examine this thing I drew on the board. Now, notice some weird parts about this graph. Let's say this, I don't know, some equation that just somehow fits this. I can't really think of one, but let's just examine it. What are the weird parts? Simple. This and this. Now, I'm pretty sure the concept I'm about to talk about kind of relates to calculus, but it doesn't seem like calculus, it just seems like a bunch of limits. But here, let's just start talking about limits. I believe I mentioned this in the video before, and if I didn't, then I have a terrible memory. But basically, a limit, when in use, describes the behavior of a graph at some point, or even all the way out to infinity. I'm not going to show you how to evaluate those limits yet. Actually, maybe I will. I don't know. But let's just start doing this. Right here, this is called a jump. Meaning that if the value doesn't exist right here, then it goes down here, which is what we call a removable discontinuity. Meaning that the graph will exist at some point, but these types of things normally exist if you have an equation in fractional form. Let's take this for example. Alright. So, when you talk about discontinuity, you have to think about it this way. Where is it that you divide by 0? Well, when x equals 3. So when x equals 3, there's something really funky happens. This brings up the idea, let's see, 3 minus 3, that's 0, 0 times that's 0, that's 0, 0 over 0. Now, you can't do this. This is what we call an indeterminate. And this is an issue. If you ever see this, then think about it this way. You can cross them out and you can get 1. But you can also multiply that by 0 to get 0. But you can also multiply it by 2 to get 0. You can multiply it by the square root of -1 and still get 0. You can go into any dimension and it's still filled up. See, the difference between this and this is that this will fill up the entire universe. Because there's no answer, because they're all the answers in one go. That's the funky part. And before I just... Here, this is not... I should probably write this... Oh, screw it. This is the limit notation, LIM. And... oh my goodness. Okay, I'm just gonna put it down here. There. This describes the behavior as it approaches 3. So it'll be like, does it approach 3 at that point? Well, it does approach 3, but then it breaks the entire universe. That's pretty much how I can describe it. Because it has so many properties that... Alright, a little linear algebra thing. So there's this thing called AX equals B that involves a matrix. If there's no solution that can fill up this thing called a null space, which means it equals 0, then that means it's all the solutions. It's such a weird concept. But let's go back to this. So when you're describing this limit, fixed quality, There we go. Alright. So, if you know how to do this, all you have to do is just cross out the discontinuity. That's where it becomes removable. But what about if you had something like this? Here, let's just erase this. Alright. 1 over x minus 2, taking the limit as x approaches 2. So, when you plug that in, is there any way you can get rid of 1 divided by 0? Well, no. So, that becomes, wait for it, infinity. Now, here's how I'm going to describe this. Because I don't think regular algebra classes teach why 1 divided by 0 could be infinity, because I think I remember something about the teacher just saying 1 divided by 0 is 0 or infinity. But the reason why that this becomes infinity, let's say we put in 1.999. So 1.999, that becomes negative 0.0001. Well, what about 1.99999? Then it becomes an even smaller number, negative 0.000001. What? I think that's how many zeros I use, or nines. But this leads to this idea called a big little concept. Here, I'll write it on the board. And the big little concept just means that if it's a fraction and it's smaller down here, then it'll get even bigger over here. It'll become a whole number. And you can actually examine this by, say, 1 divided by a million. That equals like 0.000001. But a million divided by 1, that equals a million. A million divided by 2, still a bigger number than that. Now, let's talk about polynomials. Where's my eraser? There is one rule with polynomials that you must know. Polynomials are always continuous. Although, let's define continuous. Is there anything wrong with the graph I'm about to draw? Do you see any jumps? Do you see any vertical asymptotes? That's what you should call it. There are also horizontal asymptotes, but I want to talk about that once we talk about end behavior and stuff in the next video. But the vertical asymptotes you can learn right now. But for this one, you don't actually see any vertical asymptotes because it would have been vertical, which should be self-explanatory. And they only exist in fractional form. But let's also talk about how, with this function of polynomials, when does this actually go back up? Or what if this were to go straight through? Here, let's examine the graph of x squared. Okay. Now let's examine the graph of x cubed. So, if you were to square root this one, would you happen to get a negative number? No, you can't. Every single number that you get from x squared is always going to be positive. But this one, if you cube root it, that can give you a negative number. So this leads to this idea that if you can factorization just means you break it apart into simple components. Alright, they can cut out again, so I just drew the graph I was originally going to go for. So, can you guess what exponent that variable will have right here? An odd number. So, here, I'm going to write this down. If you need to, go ahead. Through. And we're going to partition this all integers by saying n is an element. An element just means it's a part of that group. Odd. So when x to the n power that is odd, that goes through. But x, this works for integers. With other numbers, it's going to come out differently. Integers just being whole numbers. And then x to the n element even numbers, this bounces. I believe that's a term that mathematicians use, or junior math teachers. Alright, now what do we have to talk about? Well, could you tell that this is continuous all the way through? So we have some vocabulary that you should know. It's continuous, and you can use that graph as an example of this. Non-removable discontinuity. Ugh. This takes a lot of energy. I'm just going to put disk. And then removable disk. And you can apply this with the equation that I gave earlier in the video, because you just have to know how to factorize and then figure out and avoid the indeterminate form. And I believe that's the basics of Calc 1. Don't be too scared if you're just going into Calc. It isn't that hard. I mean, the applications are kind of hard, but that's just because applying things, it's always been kind of stupid to me, so it's not your fault. Alright, now I want to talk about this type of function, because we've already talked about polynomials and then these fractional functions, but now let's bring up this thing called a piecewise function. This will have the notation f of x and then g of x being an arbitrary function that you use, and h of x. And then it'll have a domain over here, normally. And domain just means the x values that you can plug in for that certain function. So it'll be accounted for on that domain with this function, and then it'll be accounted for in a different domain for this function. So we'll just put comma, 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 chameleon. Yeesh, I'm kind of stupid. Alright. Now, let's apply this back with the continuous stuff. This will relate to differentiability once you get to that part of calculus, and I hope to get to teach you guys this. Well, if anyone actually watches these videos. I don't know. Probably some 7th graders. So let's just use the idea of this discontinuity. Oh, we should probably put a hole here. That's called a hole. I almost forgot to put that down. So it's always going from hole and then jump. I could put an arrow down if that'll help. Alright. So right here, you can tell that it's not continuous, and therefore the function at that point, when taking a limit, is going to be discontinuous right there. But what about if you wanted to make it continuous? Then how would you do that? So, can't we just move this upwards? If you want these to be continuous, then plug in the values at the maximum value that you can continue on the domain and equal it to this one. And when you find out when it equals that, that's your equation. And if it doesn't equal that, then it's discontinuous. If you have to create an equation for h of x or g of x, just follow that method with only linear equations. I'm not sure if teachers do that, but I just assume that it's going to pop up in like some prep school or something. I don't know. Rich kid stuff. But I'm not sure. Actually, I'll do an example real quick. Alright. We'll use the basic x squared and an arbitrary function h of x. So it'll go from negative infinity. Oh, you always have to use those open brackets for infinities because you can never reach it. And that's always going to be the notation. Negative infinity and then 1. We'll put open bracket on that because that's when this will start using 1. So this is a closed bracket, 1, and then infinity. Alright. So what's the value of x squared at 1? Well, that's 1. That's going to be the maximum value of the domain for that part of the function. That's why it's called a piecewise function, because it's in pieces. You know? I almost blanked out. That kind of made me too happy. Alright. So what equation can we use that'll equal that? Well, you can use x. Simple. That's why you should use linear equations. If you need to use quadratic equations, just tell your teacher to stop talking. Because there's really no point. I don't know how that's going to apply. Unless you have some application, there's no point. You know, maybe you'll figure out how to explain prime numbers. I hope none of your teachers ever do that. That just seems stupid. Just coming up with the infinite amount of functions to just get 1. That just doesn't make any sense. Sorry, I've had too many run-ins with stupid teachers. Alright, now let's talk about the last thing on this video. And it's called a step function. Alright, this has a different notation from the other stuff, and maybe you'll see it, maybe you won't. Obviously, they're discontinuous. But don't worry, it's just a part of the function. I don't judge functions. Alright. Let's just write step function above it. This normally applies with integers. And you can manipulate it any way. There are floor functions, which are denoted as being x, which means that it'll go to the lowest possible number. Like, even if you're at 1.99, it'll still go down to 1. But this notation just means that it'll go to the top number. So it'll start making sense and become 2. And that's how you treat functions. But you can manipulate it with just the constants that you use in linear equations, like I showed you how to do, I don't know, somewhere in the playlist. So, you have your arbitrary constants. By the way, if you put plus c, you already automatically claim that it's a family of functions. Alright, so you have plus c, and then you can move this up and down or whatever. Alright, so it's always going to be on an interval that goes straight left from, like, let's say x plus any number that's a decimal. Well, how do I denote this? Alright, I think I'm going to run out of time with my camera, so I'm going to stop the video here, but I'll probably come up with something for the next video. So, I hope you're enjoying this. God bless you. See you in the next video.